For the last part of this tutorial, I'm gonna try to get numbers out of this simulation. So the way I'm gonna do it is I'm gonna draw a line from this point to the end of the airbox. It's gonna be a 2D cut, and in that 2D cut, I'm gonna try to plot what is the B field, the norm of the B field there. So what I'm gonna do is I'm going to data sets, and in data sets right click and get to cut line 2D. And I'm gonna start the line at the edge of the magnet. It means in X 0 and in Y 2.5. 0 and Y 2.5 millimeters because my magnet is 5 by 5. And in X, the end point is gonna be 0 and it's gonna be 10 millimeters. I can plot and I will see the line where I'm gonna measure here. So the next step is going to results, 1D, and right click and hit 1D plot group. And with the 1D plot group, I'm gonna right click and hit line graph. Going back to 1D plot, and I hit in dataset cut line 2D. And in line, I'm gonna hit cut line 2D. And I need to specify what I'm going to simulate. So I'm going here to replace expression, magnetic field, magnetic, and I'm gonna hit the magnetic flux density norm. Double click it. And I'm gonna, right now I can give it in milliteslas and plot. So at the surface, right at the surface, according to simulation, we're gonna have 180 milliteslas, and it will decrease up to 20 milliteslas. But I can also plot it in terms of the y component, because right now it's the arc length. It's just the length of that distance. But I can go to x-axis and say, give me an expression and give me y. So y is gonna be in millimeters. And if I plot, it's going to be y coordinate, starting in 2.5, and it's going to be this distance. Another thing that I can do is just for polish a little bit this simulation, I can go to coloring and style. The line is going to be solid, but I'm going to use another color, and then the width of the line, you can plot it as 4, so it's going to be a little bit thicker. And I can add some markers, and when you add some markers, you can hit a diamond, for example, and the position is going to be in the data points. So right now you're going to see where do you have a real data point in the simulation, and you see that you have pretty much good information here, not only 3 points, and this is making up the numbers. So this is important right now. But the other thing that we're going to do is we're going to compare our simulation with the simulation provided by the magnet vendor. So the magnet vendor works in Gauss. So I'm going to change this to Gauss. I'm going to plot it, and I'm going to have 1800 Gauss. And I already simulate for the distance. Let me see. Our expression for when the distance is 5 millimeters. So at 5 millimeters from the surface of the magnet, I'm having around 365 Gauss. So if I go to the simulation made by the magnet manufacturer, and I say I have an NdFeB block of 5 millimeters by 5 millimeters by 5 millimeters at a distance of 5 millimeters, what is going to be the field? So the field, it says that it's going to be like around 600 Gauss. So we already saw that the B field measured from the magnet compared with the one provided by the vendor, it was a little bit off. The vendor says that it's going to be 12 kilogauss, and we have 7 kilogauss of remanence, so it's a little bit lower than the vendor says. But From 600 to 350, we have some agreement there, and at the end, the vendor provides this field that is saying like around here we're having values of around 528 Gauss. So if you go back to the simulation and and hit surface, and you put it, you plot it in Gauss, you're gonna see that the maximum point every time, let's say around here. So if I go here and double click here, I'm gonna have a value of 1,600 Gauss or 190. So we are, of course, we are having exactly the results that we want, but not the same numbers, and it's just because when we measure the magnet from the vendor, it's not quite as, let's say, magnetic as it should be. But we have a good agreement in the flux lines and in the data that we are obtaining. So this is the simulation using COMSOL multiphysics and the magnetic modules, magnetic fields, not currents. Thank you.